You know, we're surrounded by numbers every single day. But have you ever really thought about the fact that they all follow a kind of secret code? An ancient set of rules that shapes, well, everything, from our computers to the patterns we see in nature? Today, we're going to crack some of that code. Let's dive in. So, our journey starts with a puzzle, a really old one, actually, from an ancient text. It's all about a swarm of bees in a garden. But this isn't just any old swarm. Nope. The way it behaves is super specific, and it leaves behind this trail of mathematical clues for us to follow. So right off the bat, I'm throwing the question to you. Based on the clues I'm about to give you, do you think you can figure out exactly how many bees there were? Let's see what you've got. All right, to figure this out, we've got to put on our detective hats. Because this puzzle isn't just random guesswork. It lays out a very specific set of conditions that our number has to meet. Okay, here's what the text tells us. When the swarm splits into two groups, there's one lonely bee left over. When it splits into three groups, two are left. Into four, three are left. But, and listen up, because this is a huge clue, when they split into five groups, there are 0 bees left over. So we know the number has to be a multiple of 5. Any ideas yet? Now, we could sit here all day guessing and checking numbers, but where's the fun in that? Mathematicians, they love an elegant solution. And to crack this, we're going to pull out a powerful tool that's, believe it or not, over 2,000 years old. And that incredible tool is Euclid's division algorithm. Seriously, this thing is one of the absolute cornerstones of number theory. And it gives us a really precise way to think about the very thing our bee puzzle is all about, remainders. Okay. I know this looks a little intense with all the letters, but don't worry. This is really just a super formal way of describing something you already know from elementary school. It's just saying that when you divide one number, A, by another number, B, you're going to get an answer, that's Q, and a remainder, R. And the really important part, that remainder is unique. And that little leftover number is the key to everything. This might still feel a bit abstract, so let's make it real. Picture two strips of paper, right? One is 100 centimeters long, the other is 60. Now, you lay the 60 centimeter strip on top of the 100 centimeter one. What's the leftover bit? It's a 40 centimeter piece. Okay, now take that 40 centimeter piece and measure it against your 60 centimeter strip. You're left with 20 centimeters. And for the grand finale, you take that 20 centimeter piece and measure it against the 40 centimeter one. What happens? It fits perfectly, twice, with nothing left over. That last piece you measured, the 20 centimeter one, that is your greatest common measure. Simple as that. And here's what that paper strip activity looks like in pure math. You can see it right there. 100 divided by 60 gives you a remainder of 40. Then you take the 60 and divide it by 40, which leaves a remainder of 20. Finally, 40 divided by 20 leaves a remainder of 0. Boom. That last non-zero remainder, 20, is our highest common factor. It's just a beautiful, clean process. So let's get back to our bees. We can apply that exact same elegant logic about remainders. We can sift through all the possibilities until we find the one single number that fits every single one of those clues. And that number is 35. Think about it. It's divisible by 5. And if you divide it by 2 or 3 or 4, you get exactly the remainders the ancient puzzle told us about. Pretty cool, right? Okay, so Euclid's algorithm is all about dividing numbers. But what if we try to break them down in a totally different way? What if we try to find their most basic, fundamental parts? That brings us to what you might call the atoms of the number world. Now this is one of the absolute biggest ideas in all of mathematics. It's called the fundamental theorem of arithmetic. And it basically says that any number that isn't already a prime number can be broken down into a string of prime numbers multiplied together. And here's the kicker. There is only one way to do it for any given number. It's like a unique fingerprint. A really great way to get your head around this is to think of prime numbers as the DNA of the number system. They're the basic building blocks. Every other whole number is just a unique combination of that prime DNA. For example, take the number 210. Its unique prime DNA is 2 times 3 times 5 times 7. You can shuffle the order around, sure, but you will never ever find a different set of prime numbers that multiplies together to give you 210. It's just a fundamental law of the universe. But what about the rebels? The numbers that just don't seem to play by these nice, neat rules. The numbers that kind of break the system. Well, welcome, my friends, to the wonderfully weird world of irrational numbers. To prove that a number like the square root of 2 is irrational, we're going to use this really clever logic trick. It's called a proof by contradiction, and it starts by us assuming the exact opposite of what we're trying to prove. So let's just pretend for a minute that the square root of 2 is rational. That means we should be able to write it as a simple fraction, a over b, in its simplest possible form.
Okay, detective time. Let's follow the clues. If we square both sides of our equation, we get 2 equals a squared over b squared. A little bit of algebra later, and we see that a squared has to equal 2 times b squared. Now, what does that tell us? Well, if a number is 2 times something else, it must be an even number. So, clue number 1, a squared is even.
And here's the next crucial piece of the puzzle. If a number times squared is even, then the number itself also has to be even. Just think about it for a second. An odd number times an odd number is always odd. So a itself has to be even. And if a is an even number, we can just say it's 2 times some other number, let's call it c. Now, for the plot twist, we take our new definition for a, which is 2c, and we plug it back into our equation from the first step. And when you work through the math, you find something incredible. B squared must also be an even number. And of course, that means b itself has to be even too. And right here, this is the moment our whole case just falls apart.
So, why is this a big deal? Well, remember our one big rule at the start? We assumed that the fraction a over b was in its simplest form. But wait a minute, if both a and b are even numbers, it can't be in its simplest form. You could just divide both of them by 2. See, we've just proven ourselves wrong. We've created a complete contradiction. And when that happens in a proof, it means our very first assumption had to be false. The square root of 2 cannot be written as a fraction. It is irrational. Case closed.
All right, for our last stop today, we're going to look at a tool that lets us completely flick our perspective on numbers. It's a way to solve a whole new kind of problem. So on the left, you've got something we all know, an exponent. 2 to the power of 3 equals 8. Simple. The question we're asking is, what's the final result? But now look at the right. That's a logarithm. It asks the reverse question. It says, hey, to get the number 8, what power do I need to raise 2 to? And the answer, of course, is 3. They're just two sides of the very same coin. And this connection gets really, really powerful when you look at the rules. Basically, every rule you learn for exponents has a matching rule for logarithms. You know that rule that lets you add exponents when you multiply numbers with the same base? Well, that translates directly into a log rule that lets you turn multiplication inside a log into simple addition. It's an absolutely amazing shortcut. So, from an ancient puzzle about bees to the DNA of numbers and the beautiful mind-bending logic of irrationality, we've seen that math is so much more than just calculation. It's a language. It's a way of describing the hidden rules of our universe. It gives us the tools to ask bigger, deeper questions. So I guess the only question left is, what are we going to discover with them next?